Here we're going to consider the expansion of gases, considered thermodynamically. And when I say expansion of gases, I just don't mean expansion. It's also contraction of gases too. All right, so we're going to have three examples here. First example will be the adiabatic irreversible expansion of an ideal gas against a constant external temperature. All right, let's draw a picture of that. So here will be our initial state, and here's our classic piston, and it's going to be adiabatic, which means that heat cannot be transferred to and from the surroundings, which means that we're going to have to make this container here insulated. So here's an insulated container so that no heat can be transferred. So we're going to start with that initial state. And what we're going to do is expand this gas to a final state in which the volume is increased. And again, this is insulated. And here's the insulation here. And this is adiabatic. And recall, adiabatic means Q is equal to 0. Or dq, infinitesimal heat change, is equal to 0. So no heat can be transferred to and from this process. Let's start with the first law of thermodynamics. du, let's use the differential form, is dq plus dw. All right, we'll now, as usual, start with the general equation and make some assumptions. This is just equal to dw. We're doing that because we're assuming that it's an adiabatic process. And let's put this equal to minus pdv. So we're assuming the only work we can do is PV work. And well, essentially that's it. So that's how you would calculate the energy change, the internal energy change for the process in which you just change the volume adiabatically and irreversibly. So we have a pressure here. Suddenly, actually, no, this is, sorry, let's go back here, against a constant external pressure. Okay. So we have some external pressure here. So it's there and there. So if you have a constant external pressure and no heat can get in or out, what does that mean? Somehow it must have had some energy to push this piston up. The system inside here did work on the surroundings. So what must have happened? Well, internally there must have been some temperature change, and in fact that's equivalent to the first law of thermodynamics. I mean, if you have some work being done, that energy to do that work just didn't come out of nowhere. In fact, it came from the internal energy here, because we can't get any energy or any heat coming out here. So the temperature of the gas must have changed. In fact, if you think about it, the temperature of the gas, let's see, you're doing work on the surroundings, so the temperature of the gas must have decreased. Actually, just let's see that. Remember in the last lecture, sorry, that we said U was a function of temperature only for an ideal gas. Okay, so let's make that assumption. So this implies that if we look at the differential change in U, du, that is equal to CV dt. So there must have been a temperature change here, because we have pressure, volume changes, pressures, external pressures constant, the volume is changing, so the temperature must have changed. In fact, well, let's just see if the temperature went up or down. So we have the infinitesimal change in free energy minus pdv, and we can also equate that to the infinitesimal free or internal energy change as cv dt. Okay. So we know that minus p dv is equal to cv dt. So if dV is greater than 0, so the gas expanded, this must mean that dt must be less than 0. That's a negative sign. So if that's greater than 0, this has to be less than 0. Pressure and heat capacity at constant volume are all positive numbers. So this implies that the temperature decreased in the adiabatic irreversible expansion. And it sort of makes sense from the first law. You know, you don't get energy for free. You can't create it or destroy it. So this energy that the system is using to push the piston, that came from a change in the internal temperature here. All right, that's kind of interesting. Gas cools off when you expand. Again, we made the assumption here of an ideal gas. It's adiabatic, and only PV work can be done. In that case, you find that the expansion of that gas leads to a cooling off. We'll talk about in the next section of this lecture, in Lecture 4c, using real gases. We'll find, in fact, that things are a little different for real gases. But for this ideal gas case, it's always going to cool off when you expand the gas. All right, so that's kind of interesting. So two ways to calculate the change in internal energy. It's heat capacity constant volume times the change in temperature, or pressure times the change in volume when you have an adiabatic irreversible expansion at constant external pressure. That's interesting. All right, let's consider the case now we have an isothermal expansion of an ideal gas. All right, so if we go back here, we now have an isothermal expansion of an ideal gas. Can't spell today. All right, so what we're going to do here, again, we'll draw this classic PChem picture. We have an ideal gas in here. We're now going to expand it at constant temperature. All right, so this will now be at constant temperature. All right, we said that if it were adiabatic, the gas is going to cool off. So what's going to happen, we're going to have to put some heat in here in order to increase the temperature of the gas to keep it constant. As the gas expands, if this were adiabatic, insulated, the temperature will go down. It's no longer insulated, so now we're going to have to put in some heat, transfer some heat in there in order to increase the temperature to maintain to compensate for the temperature decrease to maintain a constant temperature. So again, let's use the idea for an ideal gas. The internal energy, U, is a function of T only. All right, well that's interesting. So that if dt is 0 for a constant temperature process, this implies what? du is equal to 0. So in that case, using the first law, du is equal to dq plus dw. If du is equal to 0, this means that dq is equal to minus dw. So how much work the system did on the surroundings, that's made up for by an increase in the by transferring heat into the system. Do work here, transfer heat in here in order to maintain constant temperature. All right, so that's that case. Now let's look at this case, adiabatic reversible expansion of an ideal gas. All right, let's see what that's all about. I don't know, I won't draw the diagram. Well, all right, so go back here. What are we talking about? So now what we're doing is infinitesimally moving this piston up. So it's going to be a reversible expansion. So at all times, the internal pressure of the gas here is equal to the external pressure. Okay, So if that's the case, let's start with the first law, analyze it thermodynamically with the first law. du is dq plus dw. We're going to make this adiabatic, so that du is just equal to dw, the infinitesimal change in work. We're saying that q is 0. That's our assumption, adiabatic. Now we're going to make the assumption that we have an ideal. Well, actually, let's first make this assumption. PdV, this means that we have only PV work. And let's make the assumption now that we have an ideal gas, so PV equals nRT, so this would just be equal to nRT over V. That's what pressure is for an ideal gas, times dV. And this, we're making the assumption we have an ideal gas. So we can substitute in what P is, minus or nRT over V. We also know that, again, for the adiabatic expansion of a gas, we'll have a temperature change, so we can also calculate the change in internal energy as CV dt. Okay, so there'll be a temperature change, and the heat capacity constant volume times that temperature change will give you the change in internal energy. All right, so let's equate these two expressions for du. So we'll have CV dt is minus nRT over V dV. Now, let's integrate this. This is a temperature, so we'll bring that over there. So this would be CV dt over T. That's equal to minus nR dV over V. Now we have the variables on the right side of the equation and left side of the equation, so let's integrate both sides. This will go from T1 to T2, and this will go to the corresponding V1 volume to V2 second volume. Okay, let's make the assumption that CV is a constant, so integral of dt over T from T1 to T2. And let's furthermore make the assumption that the number of moles is constant. So this is minus nR excuse me, times the integral from V1 to V2 of dV over V. Again, we're saying this constant CV. CV does not depend on temperature. You can pull it out of the integral. And constant number of moles N, so you can pull that out. And R is a constant. We can pull that out. All right, so with that, the integral of 1 over T will be natural log of T evaluated with these between these two integration limits. So ZV, sorry, natural log of T2 final minus T1 initial is equal to minus NR times the natural log of the final volume over the initial volume, V1. All right, let's further, we already assumed we have a ideal gas, so that we can say that, remember from the last lecture, the relationship between heat capacity, Cp, is equal to Cv plus Nr, so that Nr is equal to the heat capacity constant pressure minus heat capacity constant volume. Let's substitute that in there. So now we have heat capacity Cv, ln of T2 over T1. That's equal to minus Cp minus Cv, natural log of V2 over V1. Let's pull this Cv underneath here. So this is a natural log of T2 over T1. That's equal to minus Cp minus Cv over Cv, natural log of V2 over V1, and that's equal to, let's see, divide this thing here, so it's minus Cp over Cv minus 1, sorry, oh yeah, that's right, natural log of V2 over V1. And now let's use a different symbol here. I'll just rewrite this equation up here. So we have natural log of T2 over T1. That's equal to minus. Let's use a symbol gamma for the ratio of heat capacities. All right, so Cp over Cv, we'll use a symbol gamma. Why are we using gamma? Well, that's what everybody else uses. Oh, now look what I've done. Let me sort of erase that. Okay, good. So people use the symbol gamma. We'll define this to be equal to gamma. So this will be gamma minus 1 ln of V2 over V1. And this will just be equal to, remember, A times the natural log of x is equal to the natural log of x raised to the a power. So this is equal to minus ln. Actually, let's get rid of that minus sign. Let's pull the minus in here, so this will be 1 minus gamma. V2 over V1, that quantity is raised to 1 minus gamma. All right. Oh, look, natural log of this, natural log of this. So you can take the anti-log of both sides to give you T2 over T1. Then we get V2 over V1 raised to the 1 minus gamma power. And remember, x to the a plus b is equal to x to the a times x to the b. So we can write this as V2 over V1 times, sorry, what am I doing here? I don't want to ball point pen, felt to pen, raised to the first power times V2 over V1 raised to the gamma power. Now, we have an ideal gas, so that T2 over T1, final temperature minus initial temperature at constant number of moles, we made that assumption already, it's just P2 V2 over P1 V1 for an ideal gas. So plug this expression in there, and we have P2 V2 over P1 V1. That's equal to V2 over V1. Oh, look, that's going to cancel out. V2 over V1 raised to the gamma. Remember, gamma is defined as the ratio of heat capacity, Cp over Cv. That cancels out, so we have P2 over P1 is equal to V2 over V1, the whole thing raised to the gamma. Or finally, let me just check my notes here. Apparently I made a slight mistake here. 1 minus gamma. So this should be a minus here. All right. And so that's a minus gamma there. And there should be a minus gamma. And minus, you can just flip this around to make this V1 over V2 raised to the gamma power. So finally, if you cross multiply this, we have P1 V1 raised to the gamma is equal to P2 V2 raised to the gamma. There's a bottom line there. So this, for an adiabatic reversible expansion of an ideal gas, this is the relation that the pressure and volume initially and pressure volume finally, that PV product has to, the restraints on those pressures and volumes. All right, that's interesting. Note that for an ideal gas, isothermal expansion of an ideal gas, P1 V1 equals P2 V2. But for an adiabatic reversible expansion of an ideal gas, P1 V1 raised to the ratio of heat capacities is equal to P2 V2 raised to the ratio of heat capacities. All right, so I hope I convinced you of that down here. That's for an adiabatic reversible expansion of an ideal gas. And of course, all the arguments apply for a contraction of a gas too. Here we're just using expansion because, I guess, for historical reasons. All right, that's the end of this section of Lecture 4.